Yeah, hello everyone in these difficult times. Despite all the mess that is going on around, we will continue to do science. So our Lorentz chair of 2020, Dvali, whom many of you met already during the colloquium, so I'll take a freedom not to introduce him again with all his countless list of his affiliations and scientific achievements, but just Gia will continue his interactions with us, and today he starts his lectures about axions, anomalies, and gravity. And I just want to announce that this is an online lecture, but Gia kindly agreed to give also live lectures in September if everything goes well.
Okay. Thank you very much. Again, it's a great honor and great pleasure to give these lectures. I'm unfortunately online, but okay. I mean, we have to adjust to the situation. And thanks very much for setting up this this connection. So I will, in order not to really put a lot of pressure on the system, I will switch off video during the talk. Maybe that's better. And I've never used this this way of giving lectures. I have given a couple of seminars through a different system. I don't know how questions work, but usually if there is a question and you give me a sign, I see that some comments can be written here. I'll be happy to answer during the lecture, or of course after the lecture. Okay, so then I will just start. So let me switch off the video.
Yeah, you can keep it. You can keep the video on till the connection is good. If you have a problem, you switch it
off. All right. Okay. So you can hear me well, right? It's okay.
Yeah. So far, it seems to be.
Okay. So So this is the first lecture. I'm going to talk about axions, anomalies, and gravity. Let's see how far we can go. Now the reason why I choose axion as a subject, because it's a perfect example of how field theory, effective field theory works. And in particle physics, we are trying to understand nature at different length scales. And so the best tool that we have so far is field theory, and in particular effective field theory. And so axion physics and related physics is really a beautiful example of interplay of many different things. And it's very nice as an example of how effective field theory works. And it's also very rich. It has beautiful dynamics and very interesting phenomena. So that's why I chose this topic. So let me try to introduce first a few concepts in as far as effective field theory is concerned. Of course, the building blocks of effective field theory are dynamical degrees of freedom. Okay, so we call them quantum field theoretic degrees of freedom. Now, these are dynamical entities that you can think of them as building blocks of that for understanding the time evolution dynamics of the system. Now, the properties that they have their own dynamics, degrees of freedom. They, of course, interact with each other. So there are certain rules of the game that define how they interact with each other. And also they respond to external influences if system is open. Okay. Now, the first question is, when you have a physical system and you have some problem to solve, the first question you want to ask is, what is the choice of degrees of freedom? How do I choose degrees of freedom? And so there is no universal rule. There is no recipe. There is no universal unique answer. The choice of degrees of freedom is a matter of convenience. So it depends on what are the problems that you want to answer. So what are the questions what are the problems that you want to address? So what are the questions that we're asking? It also depends, of course, on the length scales and energy scales, because we're trying to understand nature at different length scales and at different energy scales. And correspondingly, the degrees of freedom that are convenient, they change. I will explain shortly this. Now, for example, right? If we think about a physical system, air in this room. Okay, so here is our observer, Alice. So Alice would be appearing in many places. So let's say Alice is in the room, and
yeah, your microphone is off. Something happened. Just
okay. Sorry. Sorry. For how long?
maybe for half a minute or something.
Half a minute. Sorry. Okay. So what I was saying is that there is no universal prescription for choosing degrees of freedom. It's a matter of convenience. So it depends on the length scales, on the particular problem, on energy scale, and so on. And as an example, I was considering Alice, an observer that tries to understand physics of the air in the room. And now, if Alice is interested in dynamics of the air in the room, the small perturbations at large distances, I mean, the distance is much larger than intermolecular distance. For her, the right degrees of freedom are sound waves. Okay? But this description in terms of sound waves, of course, breaks down if Alice wants to understand physics at distances shorter than intermolecular distance. Okay? So in that case, the right degrees of freedom would be molecules, molecular excitations. Or if she goes even farther, then the degrees of freedom will change. Now in quantum field theory, the convenient way to describe individual degrees of freedom is to think about them in terms of quantum oscillators. So these are quantum oscillators with creation and annihilation operators. So A plus, A dagger is a creation operator, acts on a vacuum and creates a one particle state. Now this particle has a label J, and J includes everything, all possible characteristics of particles. For instance, their momenta, the spin polarization, internal quantum numbers, and so on. Okay? And this creation and annihilation operators satisfy the standard algebra, creation and annihilation algebra. Okay, so now the good degrees of freedom. So now the question is, what are the requirements for these A's? In order for these A's to be good degrees of freedom, what should they satisfy? Okay, so now the first thing is that the good degrees of freedom are the ones that are weakly interacting. Okay, so what does that mean? Think in terms of some kind of general Hamiltonian. Okay, so you have some complicated system with many different possible oscillators. Even a single quantum field contains infinite number of oscillators because there are different momentum modes. Okay. Now you have this huge Hamiltonian that generates time evolution. Okay, so this governs this time evolution of the system. Okay, and now what you do, you try to diagonalize this Hamiltonian. So there is some specific dynamics. The Hilbert space of your system is always infinite. Even a single oscillator has infinite Hilbert space. But usually, dynamical phenomena, they happen in a restricted area. of the Hilbert space. Okay, you will never explore within finite time. There is no system that within finite time can explore entire Hilbert space or even huge portion. So there's a finite portion of the Hilbert space that your system explores. So then what you try to do, you try to diagonalize your Hamiltonian in such a way that the diagonal part, okay, of the Hamiltonian is more important throughout this dynamics than off-diagonal part. In other words, interactions are less important than the free part. So in this case, we say that interactions are weak. And why do we need this? Because in this case, we can solve systems, at least approximately, in perturbation theory. Okay, so here, for instance, in this simplified version, you have Hamiltonian. It has diagonal part, the oscillator, say, a dagger, and it has interaction part. And interaction is given by some quantity alpha, okay? And here I use units in which alpha is dimensionless. And so there is also a picture in terms of Feynman diagram. So this term describes interactions. It destroys two particles, Km, and creates particles Ij. And so weak interaction means that alpha is much less than 1. Smaller it is, better, okay? Now, if it happens that you cross, but of course nature is not always so kind to us, because sometimes you have problems in which you cross the boundary. So in a part of your Hilbert space, alpha is small and then it becomes large, okay? And so in that case, you have to switch from one set of degrees of freedom to the other. So effectively what you have to do, you have to rediagonalize your Hamiltonian to go to convenient degrees of freedom, okay? But in each domain, we always try to have degrees of freedom that are weakly interacting. Those are the ones that are useful. Okay, so for a quantum field, for instance, right? Quantum field, very schematically, here I chose a scalar field. Now the quantum field contains tower of infinite number of oscillators with different momenta. Okay, so I choose only momentum as a label. And you have this dispersion. So they are characterized by dispersion relation. In other words, how their energies or frequencies are related to the momenta. Okay? And here we have to distinguish two types of quantum theories. The first category are the theories with a mass gap. Okay? So if theory has a mass gap, then in such a theory, what happens? And of course, this will be very important also for axion and QCD and everything, is that all the correlators, they die out exponentially at large distances. Okay. So in a theory with a large gap, with a mass gap, certain mass gap m, the correlators at distance is much larger than the inverse gap. They die out exponentially. And this is an extremely important phenomenon. This is one of the reasons why we can understand nature going up in energies or in decreasing distances. Now, one well-known implication of this fact is that massive particles, they cannot mediate a long-range interaction at distances much larger than their quantum wavelength. Okay? For example, right, in this room, we experience a long-range interaction, which is gravity. So we experience interaction between Earth and us, gravitational interaction. Now, the reason why we experience that is because graviton is massless. Okay? Now, for instance, we don't experience long-range interaction between us and, let's say, Earth or Moon, mediated by Z boson. Because Z boson has a quantum wavelength which is approximately 10 to the minus 16 centimeters. And so any interaction mediated by Z boson, a long-range interaction, is essentially zero. It's essentially dead. Okay? Okay, so now, in a gapless theory, the story is different. Because if theory is gapless, there is a massless, a massless field. You can mediate interactions which are long range. For example, massless electrodynamics is is a perfect example. You probably have seen it many times, but still it's good to always explain concepts on the things that, the examples that we know. For example, long-range Coulomb potential. If I have two charges, Q1 and Q2, there is an electromagnetic interaction, electric field created by them, and it gives long-range interactions. Okay. So, for instance, I chose here the gauge in which only a zero component of the field is zero, and so therefore this. And also this has to do with photon propagator. Okay. Now the classical picture, so we can understand this. Okay, let's try to understand this in classical picture and quantum picture. Okay, so in classical picture we have Maxwell's equation. Okay, so this is a famous Maxwell equation. This is a famous Maxwell equation. Sorry, this. Sorry. Can you hear me?
Yes, we can hear you fine.
Okay, sorry. Okay. So let's go to Maxwell, famous Maxwell equation. Okay. This is okay. The famous notations, everybody knows it, but let me just remind you that divergence of the F mu nu is given equal to a current, electromagnetic current. F mu nu is field strength tensor. It's a two-form, anti-symmetric two-form, and a mu is the vector potential, so the famous vector potential. Okay. Now, if I have a point source of charge q, right? So this equation famously reduces to the famous Laplacian equation for a0 in this particular gauge, and so a0 is given by the inverse r. Okay. Now, the story is completely different for massive photon. So the theory with massive photon is called Procca theory. Okay, so in that case we have Procca equation, and in this case we have mass term. It's written. Unfortunately, I don't have a pointer, but I assume it's straightforward for you to see. So first of all, I have denoted massive photon by tilde. This is important in order to distinguish it from massless one. So just to make sure that this is not Maxwellian photon, but it's Procca. And now Procca, with a point source, gives solution which is screened at distances larger than the Compton wavelength of the photon. You can see, so it falls off exponentially, the electric field. Vector potential and the electric field, okay? So now, this is classical picture. Now, the same thing we can understand in quantum picture, okay? So we can understand it very nicely. The same classical force, classical Coulomb force, we can understand as a quantum process of exchanging virtual photons, okay? Sometimes students are surprised with this, because how can it be the quantum process gives a classical picture, but that's what it is, okay? That's why quantum physics works, because it also reproduces not just quantum phenomena, but it also reproduces classical phenomena. Now in quantum picture, what happens is that if I have two charges, q, little q and large q, okay, so the force is mediated by the exchange of a virtual photon. Very good. So the way what happens, there's this cartoon below, that two charges, they exchange a virtual photon. Now the way you can understand why gapless theory and theory with a gap, mass gap, behave in a different way is the following. Okay, so the quantum intuition is the following for this. Now, in general, in virtual particles, they are not real particles. So they are what we call them off-shell. Okay, so virtual particles, the process of mediating a virtual force by virtue of particle is not a classical. It's a classically forbidden process. So one charge is not shining a classical wave that is interacting with another charge. Nothing like this is happening. Okay. So this is a classically forbidden virtual process. Now, such processes they come with a price. So what is the price? The price usually, as you know very well also from quantum mechanics, is that we pay the price of Euclidean action of the corresponding process. Okay, so higher is the action, more suppressed is the process. Okay? Now you can understand what is happening. Okay? So let's estimate the Euclidean action for a Gapless theory. So in Gapless theory, what happens? I have to shine a photon at distance r, a virtual photon. The action of this process, Euclidean action, is roughly a would-be energy of a photon of that wavelength, E, times the distance. Okay, so this is given by momentum times r, and since energy can be arbitrarily low, the corresponding system chooses to mediate photon of precisely the wavelength inverse r. Those are most convenient ones. And so the action is order 1, and there is no exponential suppression. However, for a massive photon, okay, the story is different, because for a massive photon, the same Euclidean action that is the price to pay has energy times distance, but there is a lower bound on energy. Okay, even a virtual photon has a mass, and correspondingly you have this n times r suppression. So this is the way you can understand this. So therefore, we pay for a massive particle this exponentially suppressed price. Of course, this of course we can do it rigorously in the language of photon propagator. Now, the reason why I'm discussing this, because the photons and this kind of stuff are more familiar examples. As you will see, the historic carbon copy continues, repeats in QCD in the generation of the mass of the eta-prime, in the generation of the axion mass. Okay? So the massless propagator has a pole at k square equals 0, and massive propagator has a pole at k square equals m square. And correspondingly, the exchange between two static charges in one case gives you 1 over r, and in the other case gives you Yukawa force, exponent minus n times r over r. Okay? Very good. So now, what happens now instead if I have a charged surface, right? So instead of a point-like charge, if I give you a charged surface. Well, the charged surface, what it does is that it creates a constant electric field in a massless theory, in a theory without mass gap, okay, at arbitrarily large distances, because field is constant, there is no fall-off. So, for example, if you solve an equation with a capacitor plate, which carries charge Q, so the solution is that you have a constant field on the right-hand side, then there's a jump, and the jump is proportional to the charge, and then there is a constant field on the left-hand side. So now the lesson, therefore, is very important, and this lesson is directly related to understanding strong CP problem in QCD, as we will see. The strong CP violation of the CP violation by a strong interaction force. The lesson is that in a gapless theory, boundary surface charges can create a physical effect in the bulk. Okay? So in other words, if you have a gapless theory and somebody prepares some boundary charges at infinity, those charges can have an observable effect in laboratory. You can locally measure this effect in laboratory, despite the fact that the charges are on the boundary. And this is extremely important, because normally we think that boundary terms are not so important, but actually they are when you have a gapless situation. Okay. Now, again, there's a constant contrast in the boundary in the massive theory. Even if you have a boundary charge, even if you have a capacitor plate, it will not generate an electric field at large distances. Again, electric field falls off exponentially. Okay. So here is this well-known equation. I'm sure you have seen it many times. So therefore, if your theory has a mass gap, then boundary charges should not have any local effect. Okay, so in a theory with a mass gap. And this may create a sort of seeming puzzle, as we'll see in QCD. Because boundary is always very far, and so the local effect should be zero. Now, let me comment about gauge redundancy, because this is important also. Now, as you know, I've seen probably many times, quantum field theories with spin actually higher than 1/2, even zero spin, you can rewrite as a gauge theory. So in other words, the only exception is probably spin zero, scalar, and 1/2 spin 1/2 that are not represented by gauge redundancy. All the other theories exhibit what we call a gauge redundancy. Now, so you can ask this question: is gauge redundancy fundamental? In other words, is this gauge redundancy there because we are not smart enough to choose right variables that would eliminate this redundancy, or it is fundamental? It looks like the gauge redundancy is fundamental. So it's not because we are not smart enough that we could not find the right language for describing this type of systems, but it's always there whenever we're talking about particles with, in particular, spin 1, for instance, okay? Now, the classic example is a particle with spin 1, a field with spin 1, that's Maxwell, okay? So here's Maxwell-Lagrangian with a field strength tensor, F nu, and it's an anti-symmetric, it's a two-form, and so therefore it exhibits gauge redundancy. So in other words, you can shift arbitrarily your vector potential by a derivative of a scalar function, omega. So omega is a gauge transformation parameter. Now, correspondingly, a photon propagates 2 degrees of freedom, as you know very well, probably. And the reason is, we can see it very easily. First, I can choose the gauge. For example, I can choose for divergence of the photon to be 0. Then the equation of motion, so this kills 1 degree of freedom. So this kills 1 degree of freedom simply. Then there are 3 remaining degrees of freedom. And the one out of these 3 remaining degrees of freedom, I can kill on shell now by the remaining gauge redundancy. So there is 1 degree of freedom which is killed forever, and there is another degree of freedom which is killed on shell. Okay? And so we are left with 2 polarizations. So the photon, massless for the Maxwellian photon, Maxwellian field, has 2 propagating degrees of freedom. Now, what happens in Proca? Now, in Proca, again, I'm writing here Proca Lagrangian, in which I'm denoting A by tilde, because I want to distinguish it from Maxwellian Lagrangian. Okay, so A tilde means it's a Proca field. The reason why I'm doing this, because it turns out that when you add a mass to a Maxwellian field, you are deforming a theory. And this deformation is not continuous. So in other words, in quantum field theory, we play around with theories. Very often we take one theory and we change parameter of the theory, and we get another theory. We call these deformations of the theory. Okay? So here, what I'm doing is I'm taking Maxwell and adding a master, small master. Now it turns out that this deformation is not a smooth deformation. In other words, when I'm adding a master, I'm not only that I'm modifying frequencies of the oscillators that the theory includes, but I'm also introducing new oscillators. In other words, I'm introducing new degrees of freedom. So from 2, we go straight to 3 polarizations when I introduce a master, no matter how small. And that's why I'm denoting it with a different symbol, A tilde. this is very important to understand that in the limit when mass goes to 0, A tilde doesn't go to A. Okay, so we can see this easily because in the language of A tilde, obviously there is no redundancy because I cannot change A tilde in such a way that to keep the Lagrangian the same. And because of this, sometimes people say that the mass term breaks gauge redundancy explicitly. And this is not correct. This is not a correct field theoretic statement because in order to understand whether it breaks gauge redundancy or not, first thing you have to understand what are the degrees of freedom that A mu tilde contains. Otherwise, it's like comparing apples with oranges because in order to see whether that gauge redundancy really broke, you have to compare right degrees of freedom. And actually, when you do that, you see that gauge redundancy didn't really break. So what happens is that now you can see, you write down Peccei equation, it's written here with the mass term, and if I take divergence of this equation, I get a constraint, I get Peccei constraint. And Peccei constraint simply tells me it's a constraint, it's not a gauge choice, and this constraint tells me that now there are only 3 degrees of freedom remaining. And that's it. I cannot do anything more. And these 3 degrees of freedom, actually they represent one Maxwellian degree of freedom. So A tilde I can write down as a sum of A mu plus the divergence of a scalar. So there is one Maxwellian component, A mu, but there is also a longitudinal component, which comes as soon as you write down a mass term. So phi comes there, okay? And therefore, you can see very easily that the redundancy, nothing happened to the redundancy. It just remains there. Why? Because if I shift now A mu by a gauge shift, I can shift phi simultaneously, and A tilde, nothing happens to A tilde. So this phi component is called Stuckelberg or Goldstone component. Okay. Now, it's very important to understand that this is not a different theory. This is just simply using Stuckelberg notations of the same theory. Okay, so just using the same length because a Peccei field with 3 degrees of freedom, a Peccei field always has 3 degrees of freedom. Doesn't matter how you write them. Okay, but sometimes it's useful to write things in a smart way so that then we can understand what is happening. Okay. Okay. So therefore, this is a summary of this thing. So therefore, what happens is that when I have a gapless theory of a gapless photon, and I want to give it a mass, I promote Maxwell into Peccei. Automatically, I'm endowing this theory with additional polarization, phi. So so the photon, massless photon, eats up phi and becomes massive. It's very similar to Higgs effect. The only difference is that there is no Higgs particle in this story. Okay, so it's a hard mass term, but nevertheless, hard mass term always comes with degrees of freedom, with degree of freedom phi. So it's 3 equals to 2 plus 1. This is the story, and the gauge redundancy in the original one continues. Okay, now let me move to QCD. Okay, let me say a few words about QCD. Now, in ultraviolet, so QCD is a classic example of the theory in which degrees of freedom change. Okay, it's just a fantastic example of that. So if we define QCD in ultraviolet, because normally we consider UV physics, ultraviolet physics, as more fundamental because it's shorter distances, more elementary. So if we define QCD in ultraviolet, QCD represents a theory of quarks and gluons. Okay. Now quarks I'm denoting here by size, and their index is J alpha. J is a color index. Okay. And alpha and alpha bar are so-called flavor indices. So here, just to make sure about notations, so psi bar is not a Dirac conjugate. Psi bar stands, so I'm using here, for simplicity, I'm using the basis in which all particles are Weyl spinors, 2-component Weyl spinors. We can choose them to be left-handed, okay? Or left-handed or right-handed. So when I say left-handed, so I can use either right-handed particle or a left-handed antiparticle. Okay, it's up to you what you prefer to do. So therefore, the bar simply stands for an antiparticle. Okay, and alpha and alpha bar, they are not related with each other. These are indices that are subject to different transformations. So this is a flavor group, famous flavor group of QCD, which is UNF left-handed and UNF right-handed. So UN left-handed, okay, by notation it ends on particles. The other one acts on right-handed particles or left-handed antiparticles. It's up to you the way you want to assign the chiralities. Now, the gluons are mediators of the interaction, and they don't have colors. They don't have flavor. They only have colors. So in real QCD, in the QCD of our world, there are 8 gluons. But in general, we can generalize QCD to large number of colors, and in general to NC colors, and then the number will be NC square minus 1. So gluons transform as an adjoint representation of the color group, and quarks transform as fundamental representations. So the pairs of quark and anti-quark, or left-handed, right-handed, we call them flavors. Okay, now in real world, there are 3. Strictly speaking, there are 2. U and D are the lightest. S is not terribly light, but I will include in this discussion. So I will limit myself with 3 flavors, because those are the ones that are lighter than the QCD scale, or at least comparable. Because there are other 3, C, B, and T quarks, and those are heavier. Okay, those are heavier than the QCD scale, so therefore I'm not including them into the consideration. So with 3 quarks, 3 flavors, there is a flavor group which is SU3, U3 left and U3 right. Okay, so they act on the sides with bars and without bars. Now this symmetry, of course, in real world is only approximate, because quarks are massive and the symmetry is broken explicitly. But for the moment, for the time being, I will assume quarks will be massless. Okay? Now, there is this useful double line notation introduced by Toft originally, in which you can think of this as a color flow. So, for instance, gluon is a double line that carries colors flowing in opposite direction. And for example, a gluon which is blue-red can transform a quark of blue color into a red color, and so on. And also, gluons self-interact. They interact with each other because they carry 2 labels of color. Okay, and so there is a strength of this interaction. We call it alpha. Okay, which controls the strength of the gluon-gluon interaction. Okay, this is alpha QCD. Okay, so now everybody knows about asymptotic freedom. You heard it many times that QCD is a consistent theory in UV because the coupling becomes weaker and weaker at high energies and in high momentum transfer. Okay, and correspondingly, the coupling increases towards infrared. And what happens is that it hits this point we call lambda QCD, a QCD scale, at which QCD coupling constant becomes strong. Of course, constant is not really a constant. It depends on the momentum transfer, at which scale you probe it. It depends on the scale. Okay? And so this coupling strength becomes order 1 at the QCD scale, and then blows up if you just continue. Of course, the problem is that once the coupling becomes order 1, as I said before, the Hamiltonian has to be rediagonalized, and actually we don't know how to do it in QCD. It's very hard because perturbation theory breaks down. So what happens at distances much larger than the so-called QCD length, which is approximately 10 to the minus 14 centimeters, is that QCD becomes confining. That's an extremely interesting phenomenon. Okay, it still has to be understood. there are certain aspects are understood pretty well, but okay, we need complete understanding. So what happens is the following. The way you can think about this is the following. If I take quark and anti-quark, okay, so they interact through color. You can think of it as some sort of color electric field. But now what happens is that once I take them far apart, because coupling becomes strong, at some point the field classicalizes. So what happens is that the field is getting trapped into a flux tube, okay? And these, as a result, they form colorless states. Now, if you try to stretch this flux tube further, what happens is that you create quark and anti-quark pair, and the flux tube breaks. Now, these colorless states, they are of different types. Okay, glue balls, for example, are made out of pure glue. Actually, even that is not true because there are all possible virtual processes all the time. So everybody is made out of everybody else. So it's a system which is where virtual particles are important. But roughly speaking, glue balls, even if you remove quarks from your theory, you will have glue balls. Okay, and with quarks, once you have quarks, you have mesons and baryons and other colorless states. Now, at the same time, an extremely interesting phenomena happens. Another phenomena happens that quarks form a condensate. So, what happens is that, as I said, we had left-handed and anti-left-handed quarks or right-handed quarks. We could rotate them together independently. So there was this U3 cross U3 symmetry. Okay. Now what happens is that the condensate is like a sort of a Cooper pair, like a superconductor sort of. Okay. Condensate locks them up, and quarks condense and they break spontaneously. SU3 cross SU3 group, U3 cross U3 group, down to U3 diagonal. Okay. So in other words, we live literally in the vacuum in our universe. We are swimming in the sea of this condensate. Okay. So right now in this room, our room is filled with quark anti-quark condensate, which breaks chiral symmetry spontaneously. And since this condensate breaks chiral symmetry spontaneously, we are having there waves, sound waves. Okay. So the sound waves are so-called Nambu-Goldstone bosons. Now this is generic. You probably know this many times. That every time this happens, that you have an order parameter that spontaneously breaks global symmetry. In other words, if order parameter transforms under global symmetry, what happens is that although your Hamiltonian to start with was invariant under the symmetry group, your ground state is not. So the vacuum has degeneracy. And because this vacuum has degeneracy, there are fluctuations that explore this degeneracy. Okay, and those fluctuations are sound waves, and they are massless. So from quantum field theory perspective, they correspond to massless gold excitations, massless Goldstone bosons. Okay, so this is what is happening also in QCD vacuum. By the way, how are we doing in time? So this is still. How long is the lecture? Alexei, remind me.
Yes.
Now 15 minutes, I was told. Is that the correct understanding?
Yes, it's true, yes. Mm-hmm.
It's true, right? Okay, so we have, yeah. Okay, so we have approximately half an hour. But I want to leave some time for questions. Now, so here is this what I was talking about. That QCD is a fantastic example of the situation when the degrees of freedom change. Okay, so in other words, what happened? Look, it's very nice. So what happened is that in ultraviolet at very short distances, right? We had a theory of quarks and gluons. So here is Alice observer in blue. So this is in ultraviolet. So she's observing quarks and gluons. For example, imagine that Alice is an observer. So QCD length is approximately 10 to the minus 14 centimeters. But a priori, it could be anything you want. You can write down a QCD-like theory in which the QCD length scale could be galactic size. Okay. So now imagine that Alice is a really microscopic observer. Okay. Right. So let's say Alice, the QCD scale is 10 to the minus 14 centimeters, and Alice is doing experiments at 10 to the minus 25 centimeters. Okay. So if Alice is doing experiments at 10 to the minus 25 centimeters, a distance is much shorter than QCD length, she is not affected by confinement. Okay? And therefore, she can do locally experiments with colored states. So for her, if she uses approximate S-matrix description, these states will be color states. So for her, the good degrees of freedom will be gluons and quarks. Okay? Right? Now, however, if Alice is an observer that is doing experiments at distances larger, much larger than 10 to the minus 14 centimeters, as we are, for example, we are doing experiments at much larger distances, right? For instance, LHC detectors, they are much larger than 10 to the minus 14 centimeters. So that's why, in that case, the right degrees of freedom for Alice are composites. In particular, there are also low energy degrees of freedom, really low energy degrees of freedom, which are pions. So this is what happens. Theory changes from one set of degrees of freedom to the other. And the two descriptions, they meet at the QCD scale. Now, usually when these two descriptions meet, theory undergoes this into a strong coupling, which is genuinely a technical problem. Why? Because it's like this. You have one description, you have a boundary, and there is one description. And then when you move towards boundary from that description, those degrees of freedom become strongly interacting. If you move from the other side to the boundary, the other degrees of freedom become strongly interacting. So at the boundary, usually there is nobody that is weakly interacting. So there is usually one point, one energy scale where the good degrees of freedom are missing. Okay? And so somehow we have to deal with this non-perturbatively. And this, of course, is very interesting, but it's also a technical problem. Now, as a result of this breaking, for instance, with three flavors, there is a Goldstone octet. Okay, there is a Goldstone octet, and so these are number Goldstone bosons, the famous ones, kaons and pions, and so on. Okay, that are composites. Okay, so they're made out of quarks. They all would be massless in the limit if quarks were massless. Now, quarks are not massless, but they are light. These three quarks are not really massless, but they are light, and therefore these are the approximate description in terms of Goldstone bosons is okay. And I will stick to this description in which the masses are exact zero. Okay. Now, however, you would say immediately that since the symmetry breaking pattern was we had two U3 symmetries, and U3 cross U3 broke down to U3, there must be 9 massless Goldstone bosons in this limit. But, so one is missing. There are only 8. In that limit, there would be only 8, and one would be missing. Now, finally it was shown by Toft that this missing one is eta-prime. Now, why am I bringing up eta-prime? Because eta-prime would be an axion if quarks were really massless, or at least one quark. If even at least one quark would be massless, then eta-prime would be an axion. That's why I'm bringing up eta-prime, because the physics of mass generation of the eta-prime is identical to the physics of axion, mass generation and other effects. Anomaly, mass generation, strong CP violation, it's the same, okay? Now, so therefore, I'll proceed in the following way. So I will describe this in Toft language, and then I will describe it in a different language and connect it with axion, okay? Now, here's how this happens. How eta prime is getting mass, higher mass than other Goldstone bosons. Again, we can think in terms of effective description. Okay, so now think about psi bar psi as a field that condenses, which is it is. So you have psi bar psi, a field that condenses. Let me call it phi. Okay. So the quark-antiquark pair is a composite field composed out of quark-antiquark. Now it's a scalar, and this scalar is our order parameter. Now, since quark transform left and right, or left quark and left-handed antiquark, they transform under their own flavor symmetry groups, SU3 cross SU3. This phi, the capital phi, transforms as a bifundamental. So it has one index in one flavor group, and in the left-handed flavor group, and another index in the right-handed flavor group. Okay? Now, what happens now, we know that QCD dynamics forces somehow, let's say we don't know how, but we know that that's the outcome. So the QCD dynamics forces phi to condense. And it condenses in a diagonal way. So the expectation value of phi is unity. Okay, 1, 1, 1. And correspondingly, since one index of phi is in SU3 left and the other index is in SU3 right, the product of the two is broken down to a diagonal subgroup. Okay? Now, U3 left and U3 right, you can write down this as SU3 left, SU3 right, and U1 factors, you can redistribute them in terms of so-called axial group and the vector group. Okay? And so the axial group is broken spontaneously by the condensate. So the axial group corresponds to a transformation, U1 transformation, global. Of course, this flavor symmetry is a global symmetry. A global transformation in which you rotate every one by the same phase, universally. So you rotate psis and psi bars by the same phase. Now, this rotation turns out to be anomalous. What does it mean, anomalous? You have probably heard many times, but just to remind you. So anomaly is the situation when you have a symmetry that is good at the classical level, but is broken by quantum effects. Actually, the anomaly, the ones that I'm talking about, they appear in theory with fermions. And what happens is that in the path integral, fermion measure is not invariant. Okay. So now, at the level of Feynman diagrams, you can visualize anomaly in the language of this triangle Feynman diagram. So it's a mixed anomaly in which you have two gluons merging into quark triangle. Okay. Now, since the U1 axial symmetry is global, it's okay to have anomaly because global symmetry we can break them explicitly without any disaster or any important any disaster consequences. Okay, the consequences of course will be very important, but there will not be a problem for a theory. No inconsistency problem. Okay, and as a result of this anomaly, what happens is that the current, the axial current, which is written here, is no longer conserved, and the non-conservation of the axial current is proportional to FF dual. Now, F here is the field strength. Of course, it's now non-abelian because now we are in QCD. So F here is a field strength, non-abelian field strength, okay, of QCD. Of course, all the color indices are traced. I'm here only watching the Lorentz indices. Alpha, beta, gamma, delta are Lorentz indices. All the color indices are contracted. Now, it turns out, so now first thing I want to say is that what happens is that as a result of this contraction of color indices, as a result of confinement, effectively what happens is that the dynamics, the part of the dynamics that is responsible for generation of the mass of the eta-prime, and the same would be true about axion, becomes effectively abelian. Okay? So it becomes a abelian story, as we'll see now how. Now, because we have anomaly, because of this anomaly, precisely if we rotate, if we do chiral transformation, the Lagrangian changes. So delta L is written here on the screen. So the Lagrangian changes by alpha times FF dual. Okay. Now, in order not to carry around the coefficients and pi's and anomaly coefficients, I'm constantly rescaling them in definition of FF dual. Okay. So it's a rescaled FF dual. So I call FF dual simply with the coefficient to whatever changes how the Lagrangian changes. Okay. Okay. So because of this, the U1 symmetry is explicitly broken by anomaly, but actually there is a surviving subgroup, a discrete subgroup, which is Z, a discrete group, 2 times number of flavors. Again, this is not explicit here in the rescaling story, but there is this discrete anomaly-free subgroup. Okay, so therefore we have the situation that we have U1, the U1 is explicitly broken up to a discrete subgroup which is anomaly-free. Now, let me describe how the story becomes abelian. Okay. Now, the way story becomes abelian, you can notice from the following thing. If I take this FF dual, which is written there in the upper line, a dual field strength, it's a total derivative. So you can rewrite it as a total derivative of anti-symmetrized derivative, as an exterior derivative of a three-form object. So this object is a three-form. It carries 3 Lorentz indices, carries no color index. Okay. Now it turns out, so where A's are gluon matrices, gluons are matrices because they transform under the color group. Okay. And so C has no color indices and depends on gluons in this way. So it's a 3-form. It's an anti-symmetric 3-form. Now it turns out that in QCD, this C acquires a life of its own. Okay, so it becomes an independent entity, and actually that's the one that governs a violation of strong CP in QCD. That's why I'm bringing it up, and also generation of the masses of eta-prime and axion. Okay. Now notice the analogy. It's really cool. So FF dual is literally an electric field. If I think of C as a vector potential, as an analog of vector potential of Maxwell, except it has 3 indices. Instead of 1, it has 3 indices. Then FF dual is simply an electric field of that vector potential. It will no longer be a vector potential because it has 3 indices, not 1. But otherwise, the analogy is complete. Okay. So exactly the same way as the electric field is the derivative of A0. So the FF dual is a derivative. For instance, we can choose the gauge in which C only has 0, 1, 2 components, and then it's literally a derivative of C. So there is one-to-one between Maxwell and QCD in certain sense, in a well-defined sense, that A0 in Maxwell plays the same role as C0, 1, 2. Of course, up to a gauge choice, obviously. Yeah, I've chosen this gauge. Okay? And the field and the electric field strength plays the same role as FF dual. So therefore, from now on, sometimes I will denote FF dual by E. And E is the derivative of C. Okay? Okay, very good. So now, people noticed long ago that you can add a derivative, a term to QCD Lagrangian, so-called famous theta term, theta FF dual. Okay. Now, this theta term is total derivative. Okay. First of all, it's total derivative. Secondly, you would immediately say, oh, but look, if I have this theta term, and if I have massless fermions, like what we discussed before, this theta must be unphysical. Why? Because we saw that if I do chiral transformation, the Lagrangian shifts by alpha f(2), this has precisely the same form as this theta. So, for instance, if you write down a theta term, no matter what is your theta could be equal to, I don't know, 0.5 or 0.3, I can always choose chiral transformation to nullify your theta. So therefore, theta should be unphysical. In other words, what happens is that this theta term, in the presence of quarks, should be unphysical. And this has physical implications. This fact that theta becomes unphysical when you have massless quarks, this has extremely important physical implications. Okay. Let's see how we're doing in time. Okay, in particular, the implication of this is the generation of the mass of the eta-primes. Now, without anomaly, as we said, there would exist a massless, exactly massless, Goldstone boson corresponding to this current, to this chiral current. However, now we have anomaly. Because we have anomaly, now you should anticipate that in the potential for this order parameter phi, there could be terms generated that do not respect axial symmetry. These terms are now only obliged to respect only a z discrete part, z to n f part of the axial symmetry, but not the entire axial symmetry, because axial symmetry is anomalous. Now, of course, such term may or may not be generated. A priori, you don't know. Okay, Toft showed that such terms are presumably generated by so-called instantons. Okay, but we will not enter into instantons. It's simply enough that they exist. Okay. Now, in other words, you can already make a guess from symmetric principle, because there is to the lowest order. There is a unique term that you can write down, which will not respect axial symmetry, but respect the anomaly-free part of the symmetry. So it has to respect SUNFL, SUNFR, U1 vector, and discrete anomaly-free discrete symmetry. And there is unique such term to the lowest order, and that's called top determinant. It's a determinant of phi. Okay? Now, this determinant of phi has this structure. Okay, so now there is a modulus of the determinant, which is not important for us, because that's all we need to know that it's non-zero, and it's non-zero because there is a chiral symmetry breaking in QCD, so the modulus is non-zero. And the phase of the determinant is this would-be Goldstone boson, eta-prime. And so in this parameterization that I wrote here, that's what is written. Okay, so you have order parameter that is modulus non-zero, and the phase is eta-prime. Now you see that in effective potential there is a term that that explicitly depends on the phase. And since this term explicitly depends on the phase can no longer be a Goldstone boson. It becomes a pseudo Goldstone boson, or in fact simply no Goldstone boson, because this determinant generates a mass to eta prime. Indeed, now if you plug this potential, you will see this famous cosine. So the effective potential for eta prime has this form. Okay, so it's eta prime is just once you canonically normalize eta prime, it has this form, cosine of eta prime. F of eta is the decay constant of eta prime. It's of order QCD scale. For this discussion, is not important, precise number. Okay, now two things are important, consequences. So the first consequence is that eta prime gets a mass from the anomaly. You can see it immediately if I expand this Lagrangian, if I expand this cosine. The first bilinear term of eta prime will be lambda to the 4 divided by f eta square. But second consequence is that actually vacuum is always where eta prime exactly cancels theta. Okay, so eta prime comes always in combination with theta. So this means that if quarks were massless, theta term, okay, in QCD, would be unphysical, And we can see this in two different languages. So a single quark, massless quark, would be enough. Okay, so with a single massless quark, there would be a part of the Goldstone boson which is massless and only gets mass from the anomaly. Now, and also it appears always in this combination with theta, as you can see it here on the screen, and so therefore vacuum is always where effective coefficient of FF dual is 0. So you see, the coefficient of FF dual you wrote as some constant at the beginning, but because of the anomaly it became dynamical. So it became a function of eta prime. Okay? And now eta prime always cancels this theta. Of course, it's only true if quarks are massless. So therefore, if at least one quark were massless, eta prime would be a particle that gets mass from the anomaly, from the chiral anomaly, and simultaneously kills theta. So such particles, we call them axions. So eta prime would be an axion. Now, the axion was not introduced as eta prime historically, by some reason. It was introduced as a beyond the standard model particle later, okay? Okay, I mean, the reason, at the end of the day, phenomenologically, the reason now we know that the quarks are massive. So, okay, it's true that phenomenologically, this eta prime cannot really completely eliminate the strong CP violation of the CP by this term FF dual. Now, this term FF dual, of course, is parity odd, so it breaks CP, and it's physically observable without this mechanism. So before we go there, maybe at some point I will just stop. Maybe I'll stop in, like, I don't know, 3 minutes. What's the format? So I don't know. I stop in, let's say, 3 minutes and then take questions, or what are the limitations and constraints? Alexei? Okay. Anyway. Can you hear me? Everybody can hear me? Okay.
I can hear you.
All right. Okay, so now you see how beautifully the two pictures match. So imagine you have two observers. So one is Alice, another is Bob. Now Alice could be, for instance, a high energy observer. So Alice only knows about anomaly. So the moment you tell Alice that there is anomaly, U1 anomaly, and there is a massless quark, well, Alice will immediately tell you, okay, because there is a massless quark, there is a chiral symmetry, which is only broken by anomaly. And therefore, theta must be unphysical, because I can rotate it away, simply. Now, imagine you have another observer, which only thinks in terms of low energy effective dynamics. This is Bob. So let's say Bob doesn't really know about anomaly, let's say, but it knows that there is a particle eta prime. And so for Bob, again, there is no mystery. He says, of course, the theta must be unphysical. Why? Because I have this particle here, eta prime, and it tracks theta, and it always chooses its expectation value in such a way that combination of eta prime minus theta is 0. And so that's why there is no physical CP violation. Okay, so now let's go to the third picture. I will start it and probably I will stop and then continue in the next lecture. So the third picture is a picture of a free form, a different language. So the same thing, but different language. Now, the reason why this language is powerful because it only relies on power of gauge invariance, gauge redundancy, and anomalies. You don't have to know the underlying structure of the theory. It's enough that you know the gauge redundancy and anomaly structure, okay? So for this, let me ask the following question, okay? So now, this term, so now let's remove quarks from the theory for a moment, okay? So imagine you have a QCD, which is pure glue. Now, in QCD with pure glue, if we include theta term in the Lagrangian, theta term is physical, okay? Now, imagine that you have an observer, Alice, And Alice lives in low energy, in infrared. Okay, so now Alice lives in a theory in which there are no quarks. Correspondingly, there are no massless quarks. Correspondingly, there are no massless excitations in this theory. Okay? So it's a theory with a mass gap. Very good. So it's a theory with mass gap confining. Now, someone comes and tells Alice that, look, Alice, if I include this term, theta FF dual, in your Lagrangian, you will be observing a strong CP violation, and which you can measure in your laboratory. Okay? Now, Alice should be completely shocked. Why? Because Alice knows what I explained from the beginning of the lecture. Because Alice knows that if theory has a mass gap, a boundary term cannot have a physical effect locally. So then what is this miracle that in a theory with pure glue, all of a sudden someone tells you that the boundary term, theta term, is physical? Total derivative. Total derivative is a boundary term, right? And okay, once you understand this, then we can also understand in the same language how the massless quark kills it. Now, Alice only sees colorless states. So that's why Alice is in some sense in a very powerful position, because she can think in terms of colorless states, in terms of effective field theory. So if you give Alice this theta FF dual term, immediately she can convert it into a boundary term. It's a boundary term of a three form. Now, three form has three indices and it couples to the boundary. So it's at infinity somewhere, okay? And then you are telling Alice that because of this term, she should measure non-zero expectation value of FF dual in the laboratory. Because FF dual is the only parameter in QCD that is the only relevant parameter for this experiment. So the puzzle is, how can a theory with a mass gap generate locally an effect from the boundary? This would contradict to what I told you, because again, as I said, the three form has three indices, it couples to a boundary, so it's like a source. You can think of it literally. Literally, you can take your intuition of the electrodynamics here, think of a boundary as a capacitor plate that is at infinity, and this capacitor plate is shining this Chern-Simons three form. Okay. Now, what would be the conclusion? The conclusion would be that there must exist a long-range correlator. There must exist some massless state in the theory. Otherwise, this is impossible. And indeed, it does. Actually, it turns out that this form is a massless state. It's a massless field, not a state. It's a massless field. Because, for instance, in electrodynamics, if someone would tell you the same story, you would immediately say, oh, I have a massless photon, obviously, because otherwise how can a boundary capacitor plate generate an electric field in my laboratory? So must be similar thing happening here, and actually it does. In QCD, there is this long-range correlator, CC, which has a pole at k square equals 0. Now, usually it's introduced in form of the other correlator, FF dual, which is constant. Since FF dual is constant in the low zero momentum limit, correspondingly CC has a pole at k square equals 0. Okay? This means that C is a massless field at low energies. Now everything falls into places. Now you understand what is happening. So what is happening is that if I don't have quarks in QCD, or if all the quarks are massive, then theory contains a massless three-form field. And this is an exact statement. Why? Because vacuum structure is a structure in zero momentum limit. That's when it's important. And in zero momentum limit, this is an exact statement. You have a massless three-form. And now this is this massless three-form that is bringing message from the boundary to your laboratory. That's why you can measure strong CP violation, despite the fact that theta term lives at infinity, at the boundary. This is the physics of it. Okay. Now, finally, and why don't I finish with this transparency and continue for the next lecture? So, now, again, to reiterate, what is important is, you see, I never told you who generated this correlator. It is important, it's not important for me. The only information I need to know, of course, here I'm using the existing knowledge. I means collectively, we use existing knowledge. That this correlator is in QCD, there is a strong evidence that this correlator in QCD is non-zero, FF dual. Okay? But it is sufficient that it exists. I don't need to know who contributed to this correlator. For example, there could be instantons, but could be something else. For instance, Witten argued, and Veneziano, that this can come from resummation of infinite series. The power of the effective field theory argument is that we don't care. As long as there is this correlator, inevitably, there is a massless field, massless free form. And now Alice can understand perfectly well why boundary charges are important, because they are bringing message from the boundary to the laboratory. So that's why these CP violation by strong interactions, because of this theta term, in QCD is physical. Probably this is the right place to stop and take questions. If there are any, of course.
If you have questions, just unmute your microphone and ask them.
Yeah, if you have any questions or something or discussion or whatever, yes, absolutely, yeah, don't hesitate. About any part. I mean, including the future if you want, yeah.
Well, I have actually a question which I have for a long time, and it may be very a bit difficult to discuss in this way, because you know that chiral magnetic effect that is actively studied both in high energy physics and in condensed matter physics,
right,
based on chiral anomaly. There is a long-standing issue there, because if you have a chiral imbalance which is constant in space and everything is clear, but it cannot be always constant. So once it becomes space dependent, you need to write some equations for this variable, and basically for this degree of freedom, I would say. And basically, there is a big debate, because there are two ways to write this space-dependent current for chiral magnetic effect, and one of them involves introducing an axion such that time derivative of the axion is equal to chiral chemical potential. And a big argument against this was that this degree of freedom is related to the chiral imbalance in non-local way formally, right? And I mean, obviously, it reminds very much this degree of freedom that you are talking about.
Yeah, so sure. I mean, I'm sure that there are probably connections and stuff now. However, there are also differences, because so you're talking about the electrodynamics, right?
Yes, electrodynamics. Yes.
Story with electrodynamics. Now, of course, as you know very well, in electrodynamics, in the vacuum, we don't have topological susceptibility of the vacuum. Okay.
Yes.
In other words, there is no analog of this FF dual correlator in quantum electrodynamics. At least in pure quantum electrodynamics. At least there is nobody identified any source for it. Because there are no instantons, that is one thing. That's one thing, but also nobody identified any other source. Okay, so that's why, and so therefore, from that point of view, of course, there are differences. So in other words, in quantum electrodynamics, you don't have a non-propagating, but you don't have massless three-form field. Now, by the way, three-form field is never propagating. Massless three-form field is not propagating. Okay, I didn't have time to discuss it. I'll continue in the next lecture. But because it has no propagating degrees of freedom, it's simply a field. It's like a Coulomb field, okay, with no waves. But nevertheless, it is there. In other words, there is a physical pole at Q square at K square equals 0. So we don't have this kind of thing in electrodynamics. So therefore, from that point of view, that part of physics is different. However, if you introduce an axion, axion will be axion, of course. Axion will also couple to.
But you cannot
similarities for sure. Yeah, way
sorry, but you
dual in QCD, it will also couple to FF dual in electrodynamics.
But you can still introduce a three form, which is the same, such that D of this three form is equal to F of dual in electrodynamics. Its physical interpretation is related to magnetic helicity, right? To helicity of a magnetic field. Mm-hmm. And then this Chern-Simons form dominates over Maxwell term in infrared. So you imagine
I understand, yeah.
Then you
understand what you're saying. In other words, you see, what I was trying to say is that, of course, the Chern-Simons three form may be important and may play the role.
Yeah.
That, of course, that's not what I'm saying. Obviously, also in electrodynamics, if you have a Chern-Simons three form, can play a role. The question is whether this three form has a propagator. In other words, whether there is a Green's function which has a pole at K square equals 0. So this is the question.
Exactly. Yeah.
Right, and that at least there is no known source. I'm not aware of any source in electrodynamics in Minkowski space for this type of correlator being generated. Now, if you are in the early universe and you have some high temperature, etc., of course the story may be different because if you are breaking Lorentz invariance, maybe there is effectively some correlator generated in that case. So sure, yeah, that's an interesting question. Yes. So in other words, my point was that there is no physical independent massless free-form field in electrodynamics in the Minkowski vacuum. That's the only difference. But the Chern-Simons form itself, of course, plays the role and it's important.
You are absolutely right. Probably in the medium, because chiral magnetic effect is relevant in the medium, right? It's not a vacuum effect.
Exactly. Yeah. So in the medium, the story may be different. Yes. Yeah. Right. Absolutely. No. Yeah. That's it's actually very interesting to study. Also in the medium, because you are breaking Lorentz invariance. So effectively, theory can also somehow, in some cases, it may reduce to lower dimensional story, and in low dimensions, as you know very well, even U1 can have topological implications.
Yes.
I agree.
Okay. Any other questions? I've seen that unfortunately we lost some of the people because some people were kicked off and then couldn't connect back, but still we have many people around. Are there any more questions right now? Okay, then we probably.
Okay.
So what are we going to do? Shall we continue like that, or are we going to wait till September?
I'm flexible. The question is what is the absolutely.
Let's discuss it offline. I mean, for me the quality was perfect, but some people had issues with connections.
Oh, I see. Okay.
Apparently, the total number of licenses that belongs to CERN is limited. It's huge, but it's limited. And as people are now increasing the number of conferences, you may run out of licenses. This is my interpretation.
I understand. Right.
This is my interpretation. Anyway, but Bruno tried to record this, so we will definitely put.
There was some comment. But I could not read it. It was too fast.
Yeah, we can try to do it. Yeah.
No, there was some comment from someone.
No, the comment was possibly we can work out a better way before the next lecture via the university system Kaltura. This is another video.
No, sure, yeah. I mean, you should tell me where to show up, and I'll be happy to do it.
Okay, thank you very much, Giazen. It was very interesting.
Well, thanks to you, yeah. It's a pleasure.
We'll find a way to meet again. Okay.
Thank you, Karan.
Thank you very much.
Okay, guys. Bye.